Okay, this is another suggested problem from chapter 4. This is problem 67. 467. This is a really, classic problem. I'm sure you can find this problem in all textbooks on calculus-based freshman level physics. We have an incline with a pulley, and we have two masses on the two sides of the rope that goes over the pulley. This is mass A. This is mass B. It's frictionless. It's completely smooth. Determine the formula for the acceleration of the system in terms of MA, MB, and theta, the angle it makes with the vertical. Okay. Now, this is very similar to Atwood's machine. There's a twist. One of the masses is not free, but it's actually on an incline. But the problem is very straightforward. So one way you can do this is that you can say that this has common acceleration, and there's going to be a net force on the system arising from difference of the forces acting on these two. There's going to be a force pulling this down, some gravity, and B times G. And there's going to be a component of gravity that's pulling this, MA times G sine theta. Okay? And their difference is going to be the net force on the system. I divide this by the total mass, and I get my answer. So let's assume positive direction to be this way, MB times G minus MA times G sine theta is MA plus MB times A. And you move the MA plus MB to the denominator, and you find your acceleration. And this is one way. You could do this in a more complicated way. You can add forces to this and it will still work. Like if there was friction, there will be an additional force, depending on your, of course, assumption of motion that's acting on it. If it's kinetic friction, then it's very easy. If it's static friction, that gets more complicated, but that's not very important. This does work. And because it works, I'm not going to go into more detail here, but there is another way to approach this, obviously. You could draw the free body diagrams. And for example, for mass B, there is going to be gravity plus tension. And for mass A, we are going to have gravity. We're going to have the normal force. And we're going to have the tension that's pulling this. Okay. The magnitude of these two is going to be the same. This magnitude. This makes an angle theta with the horizontal. Because it's this angle, so on and so forth. So you can write down the equations of motion and set these two equal to each other. You will get exactly the same answer. Okay? It's a good exercise. If you think that you'll have some difficulty in it, just go ahead and verify that you will get this. But otherwise, this is not something I will do here. What conditions apply to masses MA and MB for the acceleration to be in one direction, say MA down the plane, or in the opposite direction? So we chose this MA up the plane, and we got this. So if, when you make these calculations, your acceleration turns out to be negative, then you say that, okay, the direction of motion is the opposite. Right? When you plug the numbers in, you could get a negative number over there. And when would you get a negative number? Well, MBG minus MAG sine theta being negative means I move this to the other side. Of course, MBG less than MAG sine theta. In this case, this is negative. My acceleration is going to be negative. This is A down the incline. And for the opposite case, it's B A up the incline, let's say. And something like this. Does this make sense? If the right-hand side, if A is very large, mass A is very large, the right-hand side is going to be very large, and it's going to be larger, and yes, in that case, A is going to win. It's going to fall down the incline. If MA is very small, with respect to MB, then the right-hand side is going to be small, and we get this situation. Left-hand side is larger, and then B is going to pull A. It's going to go up the incline. But these are the two formal conditions for this one.